Hello and welcome to this CoastWA training module on coastal processes. My name is Clint Doak from MP Rogers & Associates and I'll be taking you through this module today. The purpose of this session really is to just give everyone an introduction to coastal processes, and in doing so what I want to talk through is starting off with mid-ocean conditions, which are the key drivers for coastal processes and sediment transport along the coastline. We'll then start to look at sediment transport itself, followed by consideration of coastal response to climate change, quick touch on coastal hazards, and then looking at some case examples to hopefully tie all of this information together. So getting right into it, and starting off with water levels. So water levels vary along our coast on a variety of timescales and due to a variety of different influences. Most people would be familiar with the tides, but weather conditions also can affect the water levels that we see. We also have seasonal variability in water levels. We have interdecadal and interannual variability in water levels, and we have long-term changes such as sea level rise. So over the next few slides, we're just going to go through each of these in a bit more detail, just to hopefully provide that indication or that background in terms of what water levels, or what drives water level change along the coastline. So taking everything that we looked at very briefly on the previous slide, what this image does is helps to just show that it's the cumulative impact of all of those different water levels or water level components that helps to give us the total resultant water level that we see at the coastline. So starting from the bottom, you can see that we have this cumulative impact of sea level rise that adds to the total water level we see at the shoreline. We then have other factors, so the storm surge, climatic cycles, which includes your ENSO, so El Nino, La Nina effects, seasonal effects, etc. So they all add to that water level. On top of that, there's the impact of the tide, and then you have more localized effects such as wind and wave setup, wave run-up, and things that helps to give the total water level that we see at the shoreline, and that's obviously critical for the safety of any infrastructure or development that sits around it. So looking at the various different water level components, we start off with the astronomical tides. So within Western Australia in particular, we experience a significant variability in the total astronomical tides, or the tidal range that we see, also in the tidal period from, I guess, the north to the south of the state. So looking at the figure on the right, you can see that we're getting total tides in that Pilbara and Kimberley region that are generally in excess of 4 metres of tidal range. In particular in the area around Derby, we're getting the second largest tides in the world, which are in the order of about 12 metres of tidal range. Tides in these areas operate on a semi-diurnal basis, so you have 2 tides per day, so 2 high tides per day. In the southern portion of the state, where we have a significantly smaller tidal range in the order of 1 metre or less, and particularly around the Perth area, we have a mixed but largely diurnal tide. So that means we generally only have 1 high and 1 low tide per day. The reason for that is reasonably complex, but it's to do with something called an amphidromic point, so the point around which there's oscillations of the tide. More detail than we need to get into here, but if anyone is interested, you can Google amphidromic point and it will tell you what that is and why that is that we have those tidal conditions that vary across Western Australia. So on top of the tide, we have storm surge. Now, storm surge can be either negative or positive, but it's basically the difference between the predicted and the measured water level. It's generally a result of changes in atmospheric pressure or wind stresses. So there's a bit of a relationship that's a reasonable rule of thumb, and that's generally for every hectopascal change in the pressure of the atmosphere, so the atmospheric pressure, there'll be about a centimetre change in the water level. So if barometric pressure increases by 1 hectopascal, there will be about a centimetre decrease in the water level, and vice versa. So if the pressure lowers, the water level will increase. So in the southern part of the state, where cyclones aren't as prevalent, some of our cold fronts may have pressure drops barometric pressure drops in the order of, say, 30 hectopascals, which might be common. So we would end up with increase in sea level of around 30 centimetres as a result. Where we get into the northern parts of the state where we have cyclonic events, and those cyclones can result in pressure drops of 90 hectopascals in severe events, then you can have a 90 centimetre increase in water level just as a result of the atmospheric pressure differences. Wind stresses are another factor. When you have winds blowing towards the coastline, they're obviously pushing water up against the coastline, and that really, I guess, pushes that water up and helps to increase the total surge that we see at the shoreline. We follow that through then to the medium and longer term water level variability, and what we've done here is just outline some of these changes that we see. So we have seasonal variations in water level that are up to 0.2 of a metre generally along the southern portions and I guess southern and western portions of the site. Largely this is due to variations as a result of, say, the Lewin current down the coastline. When the Lewin current is stronger during the summer months, you would generally have a higher water level off the coastline, and during winter, when the Lewin current is not as strong, there will be a decrease in the water level that you would see at the coastline. As a result of that, and obviously the impacts of the Lewin current, the strength of that Lewin current can also in fact impact those water levels. So that's where we have these interannual changes as a result of ENSO, for instance, which can also have, I guess, an additional 0.2 of a metre change in the total water level. We then have these things called nodal cycles. So this is more related to tidal variations. So basically the tide generated by the moon and the sun, there's a nodal cycle of how the moon actually rotates around the Earth, and there's a point approximately every 18.6 years when the moon is actually closer to the Earth, and there's an increased gravitational pull. So that is accounted for in the tide, but it does vary on about that 18.6 year cycle, and therefore you'll have periods where you have a higher water level at the coastline than normal, and as a result there will be an impact to both the water levels and the coastline. The last point that we've put down there is just sea level rise. So this plot down the bottom is basically the average annual water level recorded at Fremantle over the period where the data is reasonably reliable, and you can see that it tracked from the 1950s through to around the 1990s at a reasonably consistent level, but since that time it has increased. So the average rate of increase shown in that data is around 0.018 or metres per year, but we will also discuss this on future slides as well. So these are the predictions from sea level rise from the latest guidance released by the IPCC, so that's the Intergovernmental Panel on Climate Change. What this figure on the left shows is basically a couple of different projections, and these projections are based on different concentrations of carbon released into the atmosphere. So the blue down the bottom is quite a low release of carbon into the atmosphere, and the red is obviously a much higher release of carbon. We won't go into what all the different RCPs mean, but if you want more information on this, then I suggest you go to the IPCC website and have a look. There's a summary for policymakers on there which gives quite a good summary of it. What you can see is that if you look at the insert of this plot, you can see that over the coming 100 years or thereabouts, under a high range scenario, the middle point, which is this darker red line, gives somewhere in the order of 0.8 to 0.9 of a metre of sea level rise, but there are error bands that sit with this. So all of the shading areas are shaded areas are basically the error bands that sit around the data, with the solid line being the actual, I guess, best fit of the data itself. So you can see that we're somewhere up around 0.8 to 0.9, maybe up to 1 at the top of the error band, and down at the lower release scenario, we're in the order of around 0.5. Obviously, as we extend that out towards the year 2300, there's much greater level of uncertainty, but there are also greater levels of sea level as you would, or greater increases in sea level as you would expect. So that's the latest release from the IPCC. Within Western Australia, the Department of Transport prepared a document called Sea Level Rise in Western Australia, an application for coastal planning. So you can Google that and you can find that document. The outcome of that document is basically presented in this figure, and this is the allowance for sea level rise that should be used for coastal planning in Western Australia. So this is based on around a 0.9 of a metre increase in sea level over a 100-year planning horizon. So it roughly accords with what's shown in the highest or one of the higher concentration pathways. Important to note though that guidance, which is provided by Department of Transport and used within state coastal planning policy, is currently undergoing review as part of a health check of SPP 2.6, and that will determine the requirement for any revision of that sea level rise for use in Western Australia. So I guess watch this space in terms of when that is available. That will need to be included in any future assessment. So then we get to the setup at the shoreline. So water level can be set up at the shoreline, as I was briefly discussing before. It can be a result of wind setup, but it can also be a result of wave setup. So this figure at the top is basically showing that as you have a wind pushing towards the coastline, it can create a current within the water. That current's obviously going towards the land, and as a result is pushing water up at the coastline. How much it pushes that water up at the coastline really depends on the bathymetry, so what the seabed looks like underneath the surface of the water. If you have a really flat bathymetry that's quite shallow for a long period of or a long distance offshore, then you can have a much higher degree of setup, because the current basically is pushed forwards, but it can't return at the deeper areas. And the converse is true. If you have this current going in towards the land, but it's very deep, then it's very easy for that water to just return in a return flow back down at depths. A similar thing happens with waves. So when waves move towards the shoreline, they ultimately break, and we'll discuss this in the wave section, but as they break, there's a translation or a pushing of water from those breaking waves up onto the coastline. What that does is it sets up the shoreline above the standard elevation, so we end up with this wave setup that occurs. But then on top of that, you also have that effect of the waves running up onto the coastline, so the swash. So if you've ever walked along a beach, you will no doubt have seen the waves running up the beach and then running down. So that's the extent of that is termed the maximum extent of the wave run up that we get at the beach. So what we have in WA is a really useful tool, and I've just included this video to show where you can access real-time water level data. So this is important for coastal planners and managers, just to be able to understand what the data looks like in a real sense. So there is also wave data on this site, but for this one we've focused particularly on the water levels. So you can scroll through to this coastal data centre, and you can actually see that there's a whole range of different areas that are covered by tides. You can go to things such as this storm surge comparison chart, which gives a comparison of the storm surge, so that total discrepancy between the measured and predicted water levels at any site. And you can see if there's trends, which may be as a result of a certain event running down the coastline or something like that. There's also an interactive map that you can go to when it loads, which will show you the different locations that all of the different water levels are available for, water level recordings are available for. So you can click on these You can zoom to the locations, you can click on them and ultimately get details of what the water level is doing at any particular time. So if you're managing the coastline, it's often high water levels that will cause issues for you. So you can track this and you can see, right, are we getting a high water level as part of a storm event or any other event, and is it something that I need to be monitoring and managing proactively, I guess, if there's events that are underway or are incoming. So that's a very useful tool to get data just to see what the water level is doing. You can see in this that there was the green indicates a positive storm surge, so a higher level of water than was predicted, and the red indicates a negative, so there's a set down in water, so it's lower than predicted, as you can see here. So this grey line is the predicted water level and the blue line's the measured. So it is a very useful tool, and I encourage people to look at that when they need to undertake any kind of assessment. So when we add all of those different water level components together, we obviously end up with some potentially pretty extreme water levels. Extreme water levels are very important from a coastal planning and management perspective, because these are the water levels that can ultimately lead to flooding or inundation, as well as erosion of the beach. And we'll talk about the mechanisms for erosion in future slides. But basically, extreme water levels and the severity of those extreme water levels are determined using an extreme analysis approach. So we complete an extreme analysis of the measured water levels by basically selecting the very severe events out of that record. And what you end up with is a plot similar to what we see on the right side. So what this plot shows is an ARI, so ARI is short for the average recurrence interval. So an average recurrence interval of 10 years, for instance, means that on average you would experience that event once every 10 years. Now that's not to say at all that if you have an event then you've got 10 years until your next event. This is purely a statistical analysis. So the other way of looking at it is that if we say we have an average recurrence interval of 10 years, what that means is that every year you've got a 1 in 10 chance or 10% chance that that event will occur each year. So that other way of looking at it is actually titled an AEP, or an annual encounter probability. So I guess just it's a key thing to keep in mind, and it's something that we see quite often, is that people believe that if we've had a 100-year event, well, we've got 100 years till the next one. That's not the case at all. But anyway, out of this, what we see is that if we take, say, a 10-year average recurrence interval event, or a 10% chance of occurring every year, you can see that in this particular location, we've got a water level of about 1.17. When we go up to the 100-year event, keeping in mind this is on a log scale, this plot, the total water level that we'd see is around 1.33. So you've only got about a 0.16 metre difference in water level between your 10-year event and your 100-year event. Now this is in the southwest of Western Australia, and I guess it just shows that we don't have a huge separation between the 1, the 10 and the 100-year events. They're all actually reasonably close together. This doesn't hold true when you get into the north of the state with cyclones, where there's a much larger spread between average recurrence interval. But the key takeaway from this is that it is based on the actual statistical reoccurrence or likelihood of reoccurrence of the events. So I briefly touched on this in the previous slide, but just to really sort of, I guess, highlight the differences. When we look at extreme water levels in a cyclonic event versus a non-cyclonic event, you can really see why cyclones have the potential to do so much damage and have such an impact on the coastline. So again, looking on the plot on the left, so this is from the southwest of the state. This is actually down at Esperance. You can see there a predicted tide coming through in the white, And on top of that, you can see a recorded water level that was obviously recorded during the passage of a particular event. The plot down the bottom shows the actual residual, so the difference between the predicted and the measured. So you can see in this particular event, we had a total water level of around about 1.5 meters relative to the lowest astronomical tide at Esperance, and the total, I guess, residual as a result of that was around about 60 centimetres. So this is reasonably typical for the types of events that we get down in the southern portions of the state. When you look to the north, this plot on the right shows a water level time history associated with the passage of Tropical Cyclone Vance, which was a severe cyclone that impacted Exmouth in 1999. So you can see in the red dashed line the predicted tidal level, and then in the blue is the measured water level. So you can see even before the main peak of the storm, the total water level was some 1.2 metres above the residual. However, as that cyclone got closer and closer, keeping in mind that cyclones, the key most intense portion of a cyclone is actually quite small. As that really intense section of the cyclone approached the coast, you end up with something in the order of like 3 metres of additional surge above the predicted tidal water level. So you end up with the potential for very, very severe impacts as a result of cyclones. And just to follow that out, this is a similar plot for Tropical Cyclone Yasi, which affected the Queensland coast. And you can see here that the blue is the predicted tide, the red is the total water level, and the green is the surge as a result of the event. And you can see here that just with the surge, it got to over 5, almost 5.5 metres of total surge associated with that event. So again, very, very severe potential significant potential for impacts associated with the passage of tropical cyclones. So the other thing that we do have in Western Australia is some pretty good resources in terms of extreme water levels. So there are 2 different resources that Department of Transport have helped to procure. The first one shown on the left is basically a design event selection for coastal erosion hazard assessments, which also includes assessment of peak instantaneous water levels or extreme water levels and wave heights. So that covers the west and south coasts of Western Australia, so up to Geraldton and then all the way down south past Esperance. The one on the right is for design cyclone events, so it gives guidance on the potential inundation levels associated with cyclones at each of the different town sites, key town sites along the coastline, and it provides a few different ARIs, so average recurrence interval events that you can consider there. So they are useful references to look at to get an initial indication of what the potential impacts of severe water levels could be at your site. The key thing in all of this, though, is that the majority of the water level measurements are completed in very controlled environments. So if we look at Fremantle, for example, this green arrow here indicates the location of the tide gauge. So it's located within the Fremantle fishing boat harbours in water depths that are a couple of metres deep. And importantly, it's sheltered from both wind and wave setup effects significantly. So if you take the water level measurements like we were seeing before out of that extreme plot that gave a 10-year average recurrence interval of about 1.17 metres, then if you applied that to the coastline, you'd likely significantly underestimate the potential extent of inundation. And that's because of the additional effects of wind and wave setup that will occur on the coastline, as well as the combined effect of wave run-up. So just need to be judicious in your use of those different references where information is given about extreme water levels to make sure that you're very clear about where the measurements apply that have been used to actually generate those values, and how I guess those values may vary depending on the site that you're actually considering. So I guess, again, just as an example, with that 10-year average recurrence interval event of around 1.17 meters AHD that we noted before, on the coastline around Perth, you would probably end up with the total extent of wave run-up under that storm event being up around about 2.7 or 3 meters AHD. So there can be a big difference between those. So that concludes water levels. Now we get on to looking at waves. So there's generally two different types of waves that we're going to consider here. There's seas, which are locally generated waves by the immediate wind conditions that surround the site. And then there's swell. So these are waves that have propagated away from a system that generated them and then impacts the coastline. I'm not going to talk about tsunamis, shelf waves, etc. That's a bit more detailed and also a different consideration. So by all means, you can Google tsunamis and shelf waves and the other types of things, but we're just going to focus on seas and swell here. So to help us get through these next sections, I just wanted to introduce a couple of key concepts to you, or a couple of key descriptors, just to help us go through this. So looking at the plot, we have a few things that we want to identify. One is the wavelength. So the wavelength is the distance between the crest of different waves. So if you have a look here, we've got the crest, so the top part of the wave at point A and point B. So the distance between those is the wavelength. The wave height is the vertical elevation difference between the trough of the wave, so the lowest portion of the wave, and the crest of the wave. And then we have the wave period. So the wave period is basically how long it takes for that wave to travel from one point to another. So the crest here. So if you're saying how long does it take for point A to get to point B, that period is called the wave period. The other important thing out of it is that the wave period and as a result the wave length is also directly impacting on the speed of the actual wave itself. So we'll discuss that more in future slides. But if you can remember the wavelength, the wave height and the wave period, then that's enough to get us started. So just to give you some overall context here in terms of why waves are so important, these are a few plots that basically show the percentage exceedance of wave heights around the globe. So I'll just explain to you what I mean by that. So you see in this top plot here, we've got a 10%. So what this plot is showing is that 10% of the time, the wave heights will be larger than what is shown in that plot. So if you have a look at it, 10% of the time along this southern portion of the globe, so in the Southern Ocean, we've got wave heights that are 5 to 6 meters in height or greater. So that's fairly significant when you're talking about 5 to 6 meter waves 10% of the time around the globe. And I guess as you come up the coast of Western Australia, you can see that 10% of the time right up through to the Gascoyne, Exmouth sort of region, we have waves that are 3 to 4 meters in height. Similarly, when we go to this plot, you can see that 50% of the time we actually have waves that are 3 to 4 meters in height along that Southern Ocean. And then 90% of the time we have waves that are 2 to 3 meters or greater in that Southern Ocean band. So this band corresponds with what they call the Roaring Forties. It's basically a very severe area where you have these meteorological conditions associated with very strong winds and low pressure systems that basically encircle the globe. So the context of all of this, without getting into too much more of the detail, is just that we sit in an environment that is very, very exposed to waves. It's also why Margaret River is such a renowned surfing location. So, seas and swells. Why do we get swell and seas, and why are we considering them separately? Hopefully this plot will help to explain that a little. So what you have when you have a storm is you basically have obviously very severe winds that are blowing within that storm. As that wind blows, you end up with seas, so these locally generated waves within the system itself. So they will be very confused. They come from a range of directions. You'll see lots of different sort of periods of waves that sit within them, and it'll be quite a confused sea state, as you can see in this picture. But as that as that wind blows longer and longer, it actually starts to generate much larger waves, and I guess the level of alignment and the organisation, let's call it, of those waves becomes greater and greater, and you get to the point where you have these swell waves that actually start to advance out the front of the different weather systems. So that can sometimes be a difficult thing to grasp in terms of how do these waves actually travel away from the systems. So I wanted to just provide a bit of an example of how that happens. So on the left, we've got just a typical synoptic chart from the Bureau of Meteorology. And what you can see here is that we've got this cold front that's approaching the southwest of Western Australia. So that's coming from a low pressure system. You can see that in this black writing, the speed of approach of that cold front is about 20 knots. Now, that doesn't mean that the wind speed within that cold front is 20 knots. It means the cold front itself is moving at 20 knots. Wind speeds associated with that cold front and the low pressure system in general are generally going to be much higher than that. So you might have 40 or 50 knot winds, but the system is only moving at 20 knots. So what that means when you get to it is that system is only moving at around 10 meters per second. So if you draw your attention to this plot on the right, which basically shows the wavelength in meters or in feet if you're into imperial measurements, but I'll focus on metric. So the wavelength in meters, the period in seconds on each of these dots, and then the actual speed of travel. So if we look at a speed of travel of around 10 meters per second, which is how fast this weather system is traveling, you can see that that corresponds with a wave height of around about a wave period of around about 7 seconds. So what that means is that if we're generating waves that are in excess of 7 seconds, those waves are going to be traveling faster than the system itself. So that's ultimately why the larger longer period swell waves will actually travel away from this system. So if you have a look here at 20 meters per second, around a 13-second wave will travel twice as fast as what that system's traveling. So that's why, again, along this particularly southwestern coast of WA, we'll start off when an event's approaching with wave periods in the order of 18 seconds, and then they'll come down to 12 and 13 seconds, and we'll get a lot of wave energy in that 12 to 13 second band as a storm front approaches. But yeah, that's why we end up with those swells coming ahead of the storm fronts, and why you'll often see the surfers down there when a big event is happening, because all the swell is propagating away from that event and is at the coastline before the storm itself reaches it. So as those waves travel to the coastline, they can undergo a series of different wave transformations. So that's what I just want to touch on the next few slides. So first I want to look at the nearshore wave transformations just as a wave approaches the shoreline. So what you can see here is that we basically have waves coming in to the shoreline, and the first thing about it to note is that a wave, as it moves through, there's actually an orbital current of the water particles that I guess they oscillate as the wave goes past. So when the wave crest goes past, those waves are moving forwards, and then through the trough of the wave, those wave particles, water particles actually move backwards. So they generally stay quite still. And that wave orbital velocity, or the orbital velocities of the particles, they decrease as is shown in that pink hatching, I guess, as you get deeper. So there comes a point at depth where the impacts of the wave aren't felt anymore. Now, that depth depends on the wave period and the wave length, and as shown in this figure, generally as a general rule, when the depth of water is greater than around half the wavelength, you won't really feel, or the wave won't really feel, the impacts of the bottom. As you get closer to the bottom though, and the wave starts to feel those impacts, it changes the way that the wave behaves. So the wave starts to touch the bottom, it feels the impact of the bottom friction, and the wavelengths start to shorten. So we end up with shorter waves, shorter wavelengths, and that results in a steeper overall structure of the wave. Your wave orbitals, your wave orbitals become less circular and more oblique as, I guess, the impacts of the waves start to get squashed. You also end up with more of a translation of water, particularly when it gets into this breaking zone, where the wave gets that steep that it begins to break, and as it breaks, that water is all carried forward up onto the beach. So that's how we get as we were discussing in the previous section about water levels, these waves actually pushing water up onto the beach. It's because they get very steep, the momentum's still carrying them forwards, and all that water is pushed up onto the shoreline. So again, key point to note about this is that in very deep water, the waves don't feel the bottom, but as they start to feel the bottom, the wavelengths shorten, their velocity, they actually start to slow down, and they will steepen and actually then break and push water up onto the shoreline. So those differences in the way that a wave behaves as it starts to come into shallower water give rise to a thing called wave refraction. So refraction is when we have different depths that the wave is experiencing. So the figure on the right tries to sort of show what happens here. As the wave approaches from an oblique angle, it's experiencing different depths, say to the left and to the right, as shown in the figure. As we've just seen on the left, the area is shallower, so the wave height, or the wave, will be traveling slower than it is on the right where it's faster. So that causes that wave to bend and bend in towards the shallower areas. Swell, obviously being a longer period, refracts earlier than seas, which are lower period, and that's just due to that longer wave period and longer wavelength, meaning that it's feeling the bottom and the impacts of the bottom more or earlier than sea would. As a result, it means that the swell waves that we get are very typically very well aligned with the beach orientation, because they start to refract far earlier, and therefore they have much more of an opportunity to align better with the shoreline. Whereas the seas, they're shorter period, shorter wavelengths, they don't feel the bottom until much later, and therefore the opportunity for those waves to bend around is much less. So that's an important consideration when we start to look at the actual sediment transport dynamics around wave-induced actions. So a key part out of that is that the figure on the top obviously only considers a very simple beach shape, but where we get into more complex bathymetries, so complex seabeds that include reefs, banks and channels, they can all impact the angles that waves arrive at the beach. So the figure in the bottom tries to sort of show that if you have shallower areas in the middle, then waves are going to basically try to wrap around into that area as they slow down, and there's certain areas where it can create nice little crescent beaches where a lot of the wave energy has been dispersed and ends up impacting onto the headlands, and you end up with quite quiet beaches. So that's just an example of how those waves can be impacted by different reefs, and there's plenty of examples of that along the West Australian coastline, which we'll show you in future slides as well. So another key component that we want to look at, or key wave transformation, is wave diffraction. So diffraction occurs when a wave passes through a gap or around a structure. So as you can see in the figure on the left, if we have waves coming through, we have a gap in the structure, waves will pass through that gap, but then once they do, they will ultimately spread out on the other side. And the way that they spread out, again, depends on the wave period. So swell will generally spread much more readily than seas. So just to give an example of why wave diffraction is important, this is a figure from Geraldton, so this is on the northern side of the Batavia Coast Marina. This is before any of the current works were done. When the Batavia Coast Marina was built, there was a spur groin that was built on the northern side to try and hold sand in place and help to manage things. However, there was a constant impact that this shoreline was eroding. So when you actually have a look at that and you see these directions of the waves as they come in and the alignment of the wave crests, you can see that they're reasonably straight. The swell waves are reasonably straight and reasonably aligned here. But as they come into the coastline, you can see that they end up with an alignment as I've shown in that red dashed line. Now, what's the impact of that alignment? Well, you can see quite clearly that the wave is actually impacting at or in the area just behind the breakwater before it impacts anywhere else along the shoreline. But what that means is that wave's actually starting to break here, and as it continues to break along the shoreline, it's actually got an effective angle that's pushing the sediment in the directions of the arrows that we've shown. So even though you might think that you're in a really sheltered environment in behind that breakwater, the wave diffraction effects are actually resulting in a push out of that sediment from that area and around the coastline, just because it basically was setting up a wave direction or a direction of wave breaking that favoured sediment transport in that direction. So it's a key consideration that we need to make when we're looking at structures. It's not always as simple as just saying an area is in behind a structure and therefore it's going to be protected. So another key component of waves and how they impact different things such as sediment transport is wave directions. What we've done here is just pulled out wave directions for a period from the CoastWA wave data, so CoastWA wave buoy. So you can see here just a whole collection of different wave directions. So it's just all the directions that have been recorded. If we filter those wave directions and filter out the data that is a wave height of greater than 0.7 of a metre, then you can see that there's a real focusing of those directions. Now, it's probably not surprising that waves with heights of greater than 0.7 of a metre are predominantly coming from offshore. So they're coming from between 180 and 360 degrees. So that's south through west to north. Now, the reason we filtered them out at approximately 0.7 of a metre as a wave height is because that's generally where you're going to start to see some much increased or significantly increased volumes of transport of sediment along the shoreline. So you can see with that there's a little bit of a trend in terms of how things vary. And just to highlight that, what we've done is we've pulled out the winter data. So in winter, with a wave height of greater than 0.7 of a metre, everything is green. And in summer, you can see all the red that's remaining, so everything with a wave height of greater than 0.7. So you can see there are these very distinct bands of shifting directions in terms of wave heights and directions during summer and winter. And as an average, you can see that during winter, these seas along the Perth coast average around about a direction of, say, 280 degrees or thereabouts. But during summer, we're probably down at around 240 degrees. So that's significant in terms of sediment transport potential along the coastline. When you look at swell, it's a different story. So swell in at Cottesloe, you can see there's a lot of scatter, but it's very, very consistent around about that 260 to 270 degree direction. It's very consistent. Just to give you an example of both of those, so this is average sea and swell directions, and this is actually from the Rottnest buoy. You can see the blue line shows the swell. There's very little difference in direction of swell throughout the year, but the seas in the green dotted line show a significant variation in directions. So again, just an important point to note, particularly when we start to look at sediment transport pathways and sediment transport rates along the coastline. So finally, just to look at waves, I just wanted to bring up this and show you this resource. So within the Bureau of Meteorology, they have a forecast feature as part of their AusWave model. So this is actually forecasting wave heights, and you can see it going through here, forecasting for approximately a week into the future. You can see in this event, there's this very significant event that's travelling to the south of Australia with wave heights in the order of 10 metres at its peak. Obviously, there's another event coming through, this event not quite as severe, and that one's up in the order of 6 metres. So this is a very useful tool, again, for coastal planners and managers to look at and be able to forecast or to see the forecast of what types of waves are going to be coming at you in the coming week. So again, if you've got an area that you need to manage, you can actually look at this data and see what's coming and do you need to take any proactive steps to manage whatever it may be because of the incoming wave conditions. There is also recorded data, as I said before, or measured data available on the Department of Transport's Coastal Data Centre website, which we looked at before with the water levels as well. So they're both really useful tools just to help you understand both the current measured as well as the future predicted wave heights that you can see in this forecast. And that's just an extract of the data from the Coastal Data Centre available at Department of Transport. So this is the example from Cape Naturalist. You can see here where Cape Naturalist sits. It shows you the location of the buoy. It shows you the direction of the swell in the red and the sea in the green, and it gives you those actual individual wave heights. So the sea wave height is 0.88 and the swell is 1.42, and the actual point of the arrow shows you the period. A time history plot of that over the last few days is also contained, as well as the history of the direction. So you can see here there were much higher events, much higher wave heights earlier in the week, and it's now decreasing down to lower wave heights. The swell period was in the order of around about 11 to 12 seconds, and the seas were in the order of around 5. So just a really good resource to be able to see what sort of wave conditions you've experienced, particularly if you notice any issues that you need to deal with. You can see what actually caused it. The last thing I want to talk about in terms of waves is just annual variability in the wave climate. So As with everything, there's variability in the meteorological conditions, and that varies from year to year. Obviously, that impacts the waves themselves, and what we're trying to show in this plot is just the 4 key events that we experience along, say, the southwest of Western Australia. So if you break that down, we have just general swell events, we have sea breeze events, we have storm events, and we have severe storm events. So if we look at that year on year and the relative proportions of those events, everything hatched in the blue is the swell, the orange is the sea breeze, the grey is the storm, and the yellow is the severe storm. You can see there's variability, but one of the key things that I just want to point out to you, because it's relevant for what we're going to discuss in the future, is that you can see there are times when there are actually very small number of storm events. So it's these variability. You might say that a very small number of storm events is a great thing for a beach because it means there'll be less erosion. That's not necessarily the case when we actually get to looking at longshore sediment transport. But I guess equally with that, there are some times when we have really significant numbers of sea breeze events as well, and even down to more severe or a higher number of severe storm events. We've discussed the waves that have been generated by local and remote meteorological conditions. The other key thing to consider is the impact of boat wake, and this is particularly relevant for riverers and estuarine environments where naturally occurring sea and swell waves aren't overly severe. So there's a number of different studies that have been done looking at boat wake. I've included some of the results from one of them here. As you can see, so this plot on the top right shows the maximum wave heights that are generated as a result of different types of boats and vessels as they move along next to a recording device at different speeds. You can see that in some of these vessels actually generated wave heights that were up to 0.8 of a metre in height, and some of them generated periods in the order of, say, 4 to 8 seconds. So these are potentially significant waves that you may need to consider in different areas because of the impact that they can have. And you can see that in the photo down the bottom, where you've actually got some quite significant waves that are impacting the river wall along Mounts Bay Road. So it's something that needs to be considered when you are looking at those estuarine and river environments. I guess you do have the potential for waves to be generated that are more significant than you could get from natural processes alone. So we move on now to currents, and there's a few different types of currents that we want to talk about here. So we have the wind and wave generated longshore currents, we have tidal currents, and then we have riverine estuary currents in there as well. An important thing to note here is that we often get asked in the work that we do what the direct impact of the Lewin current is on the coastline, and particularly on the sediment transport. It's important to note that the impacts of the Lewin current and other large-scale oceanic currents are generally much further offshore than will impact the actual, say, sediment transport on a coastline. So the Lewin current is not something that we're going to talk about or consider in terms of these nearshore processes, these coastal processes that we're talking about here. So the first type of current that we want to talk about is a longshore current. So longshore currents, as shown in this diagram, are basically generated where we have waves that are approaching the shoreline from an angle, or also winds that are blowing oblique, so at an angle to the shoreline. What that does is it basically sets up a current that helps to move, or that moves along the coastline, and that can no doubt have an impact on sediment transport and things, as we'll discuss in the next section. We also have tidal currents. So example here is just from Shark Bay, and what you can see through here is some very distinct flow paths or channels that have been created in and around the islands and across these banks. There's some modelling that's been completed in those areas, which basically shows the current speeds associated with different tidal conditions. In this, the larger the arrow, the higher the current speeds. And you can see that we've got some very large currents coming out of this area. And what that does is actually helps to erode through these banks and creates some scour channels as a result of the currents themselves. On the right, you can see this other example of I guess, the currents actually causing the formation of what are called deltas, so formation of sediment bars in and around the entrance to these river or creek mouths. So we have two different types of bars that we refer to. There's an ebb tide bar, which is generally on the outside, so as the tide ebbs and begins to flow out, it brings with it some sand, and that sand is deposited on the coastal side. And then we have a flood tide bar or flood tide delta that is basically, as the tide floods in, it pushes sand in and creates these deltas on the upstream side. Those currents and waves, though, where they interact, can result in some really unique landforms, and we can see this in and around Carnarvon, where you've obviously got some flows that happen within the river system itself. They bring sediment out into an area where waves can impact it, and then we have a longshore transport which is driving the formation of these different structures or beach formations. So you've got all these different processes that can work together to create some very unique landforms and things that require management, particularly when we are trying to get boats into and out of these different areas safely. So that concludes the discussion about the actual processes, the driving processes themselves. What we want to talk about now is just the overall sediment transport. So we'll jump into that now. There are several broad categories of sediment transport that we want to consider in this module. So the first of those is longshore sediment transport, often referred to as littoral drift, and that's basically the movement of sediment along the coastline. We then have cross-shore sediment transport, so this is the movement of sediment basically perpendicular to the shoreline, so onshore or offshore. We then have wind-blown sand transport, so aeolian transport. This is basically, as the name suggests, where wind blows sand or sediment around and ultimately creates the formation of dunes or dune blowouts, as the case may be. The last one that I want to talk about is onshore sediment feed. So this can be kind of caught up in a cross-shore sediment transport as well, but it's probably worth just focusing on it specifically because of the types of features that it can create and as well as the impacts that it can have on the shoreline. Key point to note with all of this is that sediment transport rates are heavily impacted by sediment grain size, and I guess there'll be more detail on that in future modules, but it's important to note that obviously a larger or heavier sand is probably going to move less than smaller, lighter sediment. And it also results in different formations on the beaches where you have larger, heavier sand particles. They will generally result in a steeper beach face or a steeper slope on the beach than your smaller, lighter sediments. So we bring that now to the figure that I showed before in terms of longshore currents, and this figure also helps to explain the longshore sediment transport process. So if we focus on this figure first, we have waves that are approaching the beach at an angle. As those waves approach, they obviously run up the beach, as shown by these arrows, and they're pushing sand as they go, and then as the waves draw back, they also draw back at a bit of an angle to the beach. So you'll end up with this zigzagging of sediment along the coast. Now, where does that happen? This figure on the right is a great figure that comes from the Coastal Engineering Manual. Don't focus too much on the formula and things. I don't want to lose people with this, but hopefully we can explain this in simple terms. If you look down the bottom, this cream hatched area is basically the shoreline and the bathymetry of the beach. So it's a beach profile. The area that I've shaded blue is the wave height that results as a wave comes in. So just looking at this section for a second, you can see we have wave heights coming in. The depth is getting slightly more shallow. As the depth is shallowing up, that wave height's starting to shoal a bit. You can see a slight increase in the wave height, and it gets to the point where that water depth that's available means that the wave starts to break. We then get over an inshore bar and the wave height remains stable, and then again we get to the point where the wave or the water depth is no longer able to contain the wave, and that wave starts to break. So these are the two areas that I've noted as wave breaking. This top part of the plot shows the actual rate of sediment transport that occurs as a result of this. So as you can see, where we have this zone of wave breaking, the amount of sediment transport increases significantly. Outside of these areas of wave breaking, there's very little actual sediment transport. So the key thing about that, as we were looking at the wave transformations from the offshore to the near shore, is that when waves break, they get steep, they start to translate, so they move, the water moves forward with the wave. As it's doing that, that breaking is a turbulent process that helps to stir up the water, and as it does, it actually carries that sediment with it in the wave breaking. So it's a very key item to note that the vast majority of sediment transport occurs where you have wave breaking. And if you don't have wave breaking, then the rates of sediment transport in those zones are going to be much lower. So this is an example of that. So this is just a section of Mullaloo Beach, an aerial photo from the northern portion of Mullaloo Beach. You can see that we've got waves that are approaching the angle, approaching the shoreline on an angle. In these offshore portions, you can't really see wave breaking, so you don't have these areas of white water that show the turbulence associated with the wave breaking, and you don't really see much in the way of sediment transport. When you get into these shallower areas where the wave is breaking, you can see that there's a lot of different suspended sediment within those zones, and that is where that wave is breaking. It's moving that sediment, and in this particular case it's moving the sediment to the north because of the angle that those waves are approaching the shoreline. What that means is that if we put an interruption on the shoreline, such as a groin, we end up with a situation where we can block that sediment transport and we can create a wider beach on one side but a narrower beach on the other. And in this figure you can see quite clearly the angles that the waves are approaching the beach, and you can see that as that wave's broken, particularly on the lower part of the screen, that you can see the sediment that's been picked up and suspended as a result of that, and then is being pushed to the north. You can see it quite clearly coming around the groin itself because the shorelines are created to the extent where the sand is now bypassing that groin. So we move on now to cross-shore transport. So it's typical that during winter beaches will undergo some form of erosion in response to storm conditions. It can be due to a single storm event or a series of different storm events. That recovery, so the beach can recover as a result or following these storm events, but it needs the right wave conditions to do that, and that's what we're going to talk through in future slides. Key thing out of it though is that the recovery of the dune, if a dune's eroded, can take a whole lot longer, and again we'll discuss that in the future. But just looking at this figure here now, what it basically aims to show is that in this top portion you can see the sort of normal water level, normal wave heights and normal profile of the beach. When we get high water levels, we end up with the waves actually acting on a portion of the beach that aren't normally vulnerable to wave attack. So this can mean that the wave is actually impacting the dune. Now the slope of the dune is such that it's not able to withstand the impacts of waves as readily as the more shallow or gently sloping face of the beach. So when the water level actually is high enough that the waves start to impact on the base of the dune, that's when you can see some significant erosion beginning to occur. Over time, what happens is that area of material, or that portion of material that's eroded from the dunes, is actually deposited offshore. And as you can sort of see here, it results in the formation of a bar. Now, that bar is a protective element for the beach in some respects, in that it's actually causing the waves, or it actually causes the waves to start to break earlier or further offshore than they would have otherwise. And it's a protective mechanism for the beach, whereby once that bar is formed, the waves break earlier, there's less wave energy to then impact the upper portions of the beach, and therefore the rate of the erosion does decrease. So that's part of the process that happens over a winter period in response to these different conditions, is that you often get the formation of bars offshore from a beach, which is great from a surfing perspective, but it has a purpose for the beach in terms of actually helping to prevent further erosion of the profile. You can sort of see that in these images here. So this is the same portion of beach just down to the north of Mandurah, and you can see on the left this is a typical summer profile. On the right is a typical winter profile. So the key thing to note here is that on the summer profile you can see, well, through here there's a swell wave that's coming in, and you can see in the white water the portion of the wave that's actually breaking, and that wave is breaking right up on the beach. In winter, you can see that we have waves breaking much, much further offshore, and there's a really wide section of white water, of wave breaking. So this is where these bars have formed, and you can very clearly see the difference in the beach width. So the beach width during summer is very wide, and in winter is far more narrow. So that's just indicative of the fact that we've had erosion of this beach berm, which has been pushed offshore and created these bars, which are now breaking the waves offshore and limiting the extent of the erosion. The important thing to note with this is that the sediment, while it may have moved offshore, has now actually not impacted on the dune system itself. So I've just highlighted those couple of different bushes or shrubs just to show that actually the position of the dune hasn't changed in any of that. It's just the beach berm that has been lost as a result. So we get now to this I guess notion of destructive versus constructive waves. So we'll look first at destructive waves. So a destructive wave is a wave that actually causes erosion of the shoreline. So this is, if you like, the typical sort of winter storm events that we get that erode that shoreline and help to create this offshore bar. So typically, as indicated here, we're talking about short wavelengths. So there's a high frequency of waves. You're getting, say, 10 to 14 waves per minute. So you've got wave periods that are in the order of around 6 seconds or less as a general rule. Again, we're talking quite generally here. So what we get then is we get these very steep wave fronts. We get waves that break up on the coastline, and then we have because they're quite short period and short wavelength, we have a weak swash up, but we do get very strong backwash that helps to erode that sand from the beach. And when it erodes that sand from the beach, it actually creates this offshore bar where the sand is deposited. So again, just to summarize that, we have waves periods that are in the order of about 6 seconds or less. We end up with very steep waves. They plunge on the beach. There's a strong backwash that's pulling that sand off and pushing it into an offshore bar. So the constructive wave, on the other hand, is basically a wave that is a lower frequency. So it has a higher wave period. We're talking about wave periods that are probably more like 8 to 12, 13 seconds along the Western Australian coast. So we can have low wave heights. We can have gently sloping wave fronts. And when those waves actually run up on the beach, because they have a long wave height, a long wavelength, because of their higher period, they actually do push a lot of water up onto the beach, and comparatively, the amount of backwash that you get is relatively weaker. What that does is it actually pushes that material up onto the beach, and we come up with these things that we refer to as swell-built berms. So that's where we have these really wide berms that we've seen in summer, as I showed on the previous slide, that basically are just formed by this constructive wave process. So it's important to note that we have different types of waves that cause erosion versus, I guess, accretion back onto the beach. They can happen, so you can have constructive waves that occur in between storm events, but generally from a seasonal perspective, you'll end up with a higher proportion of destructive waves in the winter and a higher proportion of constructive waves in that summer period where we have just swell events coming through. The outcome of all of that, though, is that when we do have these summer periods of I guess wider beaches as a result of these constructive waves, we also typically have very strong winds and dry sand on those beaches, which leaves those beach areas vulnerable to windblown sand impacts. So that's a good thing in terms of winds blowing and actually picking up sand and depositing it into a dune system. So we actually can help to form a dune as a result of that. And that is a really important process, as I say, because we want to build up, or generally dunes are a good thing. The not great element out of it is that the amount of sand transport as a result of wind-blown impacts is much lower and much slower than what can be experienced during a storm event. So even though a storm event may be able to erode 4 or 5 meters of dune within a few hours, it can take many months, if not years, to build up that amount of sand again as a result of just wind-blown sand transport alone. So the negative component of windblown sand transport is where we have formation of dune blowouts and the like. So this can occur when we have a destabilisation of the dune system. Could be due to, say, 4-wheel drive impact on a beach, which has damaged the vegetation and therefore opening the dune up to erosion by wind, or could be down to things such as rabbits eating the vegetation and therefore allowing the wind to actually cause these dune blowouts. As you can see in this, there's a quite extensive sort of dune blowout that has occurred, and that can be problematic if you have infrastructure located close to these areas, because you can actually have, I guess, development that's impacted or inundated by this sand as it's blown around. So this figure that's shown up on the right is basically just, it's showing an area of the Southgate Dunes in Geraldton. What we've done in this particular area is used aerial photography to generate some topography, and that's what's shown in the coloured hatching. So the red hatching is high elevations, and the green through to blue are your lower elevations. What I want to show in this video is just how dynamic these dune systems can be and how much they can move. So if we play this video, you'll see that it just steps forward over time, and you can see this migration of the dune ridges over time. So I'll play that again. It's just at distinct steps, and there's 12 years between the start and the end of this video. So you can see that these dune systems are moving to the north. The key thing to note is that they've moved to the north quite significantly over that 12-year period, and you can see the estate that sits just near it. If not for the sand mining operation that occurs in the northern portion of the Southgate Dunes, this estate would have been inundated by this sand. The other important thing to note about this, just in terms of the sediment dynamics in Geraldton, is that you can see there's two different portions of the dune. You've got a northern portion and you've got a western portion. As we saw when the video ran, the majority of these dune ridges are moving to the north. That means that in this particular area, in the northern portion, they're moving to the north, and there's not a huge amount of impact on the local sediment dynamics for the coastline, although some material during easterly winds would be blown and deposited into the water and would ultimately help to feed the sediment transport or feed the sediment budget along the shoreline. In this portion that we call the western portion of the dune, when that material migrates to the north, it actually feeds directly into the alongshore sediment transport process and the sediment budget, and therefore provides a source of sediment to that overall system. The bad part out of it is that as this sediment supply is exhausted, as the dune continues to migrate to the north, eventually there'll be no longer a supply of sand from this area, and that will have flow-on effects up the coastline where there will be less sand available, and may therefore result in erosion of those areas. The last type of sediment transport that we want to talk about is onshore sediment feed. So sediment can be transported onshore from offshore sources, and it can result in the formation of different features on the shoreline, although these features may be intermittent in terms of their timing. The key thing about it is that sediment from offshore sources may not provide a reliable or consistent feed. So whilst they may be there at a point in time, there's no guarantee that they'll continue to occur into the future. So the example in the figures is from the Dunbay Bar, which is along the Bustle and Dunsborough shoreline. You can see here there's a really distinct line of sand. So there's a sandbar offshore. As you can see over time, that sandbar eventually intersects the coastline and starts to provide a feed of sediment directly onto the shoreline, and as a result you get this salient feature or this bump in the shoreline that's resulted from it. A few years later you can see that there's still this feature, this salient feature on the shoreline that's been caused predominantly by the impact of this onshore feed of sand. It's a good example of what an onshore feed of sediment does do. The key part out of it is that historically there's been a lot of times where these features have actually occurred or been present, and people have gone and put development on them because they're obviously a nice sort of vantage point along the coastline. The challenge is as soon as that supply of sand is removed or is diminished, you end up reverting back to something that looked like it probably did originally, and you can end up with significant issues in terms of trying to manage the erosion that occurs as a result of that reshaping of the shoreline following the reduction in the onshore sediment feed. So when we put together all the different sediment transport pathways that we've discussed, you end up with an overall sediment budget. So this figure just tries to sort of show the key components of a coastal sediment budget. You've got a longshore transport, you've got transport into an area, out of an area, you've got cross-shore transport, you've got wind-blown sand, you've got blowouts. You also have potential loss due to inlet filling and other things which we haven't discussed today, but that is a process that can occur in certain areas. I guess the key part out of this is to just illustrate that everything is connected. So we have a longshore transport, we have cross-shore transport, that it's all interrelated, and the impacts on the beach I guess need to be considered in totality rather than just one component versus the other. So it is a key consideration when you are looking at the stability of a coastline or a shoreline is how do all of these sediment transport processes interrelate to result in the overall sediment budget for a shoreline, and that's what needs to be considered when you're looking for planning for future infrastructure or development. So to conclude this discussion on sediment transport, it's worth just I guess summarising everything and providing some context. So the net sediment transport along a coastline is generally the resultant of two different seasonal regimes. So we'll generally have a summer regime and a winter regime, or it may be a wet season or dry season regime. So as an example, we generally, I'm talking along the western coast, so the southwest coast, we generally have a northerly transport of sediment in summer driven by sea breezes, and a southerly or southward transport in winter driven by the northwesterlies associated with the approaching fronts. These seasonal transport volumes can be in the order of 100,000 cubic metres on exposed coastlines. So you may have a movement of 100,000 cubic metres to the north in summer, and you might have, say, 90,000 cubic metres to the south in winter. So that means that you've got, say, a total net, so the resultant over that year, of 10,000 cubic metres moving to the north. So you can see the balance is very important here. If we have a very well-balanced system, then the impacts of different meteorological effects can have or cause changes in the overall sediment transport, which can be significant depending on the situation, and we'll cover that in some of the case examples. It does also mean that the sediment isn't necessarily going to be where you want it to be. So we've got some examples here from Cottesloe. So if you look on the left, we've got an aerial photo from Cottesloe in October 2022, and you can see you have a really nice wide beach. So this is around the end of winter, where we've had obviously a lot of northerly or northwesterly events that have caused this southward transport of sediment and deposited that sediment really nicely in the embayment behind the Cottesloe groin. The unfortunate part is that when we get to February, which is one of the busiest, if not the busiest month for beach use, you can see that sediment's largely been moved. So it's the summer sea breeze has actually pushed that sediment back to the north to the extent where there's very little sand in front of the Indiana tea rooms. So much as we understand the process, it just shows that you're not necessarily going to have that sand where you want it to be just because of the way that these processes function. So we move on now to the coastal response to climate change. Now, we've already discussed the different projections and different potential increases in sea level that can occur or may occur into the future. Generally within Western Australia, something called the Broome Rule is applied for coastal planning. Now, that Broome Rule is premised on maintaining the nearshore slope by erosion of material in the upper portion of the profile and deposition of that material into the offshore area. So if we look at this figure on the right, you can see that there's an initial profile that sits here. And as that water level increases up to that point, what tries to happen is that profile tries to shift with it. So you can see that profile there in the solid line shifts up to where the dotted line sits. And as a result, there needs to be erosion of this area shaded grey and deposition of that material into this area down the bottom to basically maintain that nearshore slope. So you see that in this bottom part of the figure, where you've had erosion of this upper area and it's deposited in this lower area of the profile, therefore resulting in the same cross-shore profile, just at a higher elevation of water level. As a general rule of thumb, which is applied to coastal planning and used in the state coastal planning policy, a 1 metre rise in sea level will result in 100 metres of erosion of the shoreline. Now that's, as we've said, it's the Broome rule is based on a slope. The majority of the slopes within and around the coastline are not 1 in 100 slopes. They're probably more typically in the order of 1 in 30 to maybe 1 in 50. However, as I said, the state coastal planning policy uses a rule of thumb of 1 to 100, and that's based on trying to account for the other unknowns in climate change impact, which could arise out of differences in strengths of summer sea breezes or other factors. And some of those factors we'll discuss on the next slide. So there are factors such as nearshore wave heights changing due to increased transmission over reef systems. There are changes to sediment transport patterns that could occur due to changes in nearshore wave climate. There are longshore sediment transport rate changes that could result by changes in strengths of seasonal winds. There's all these different things that are complicating factors, and if you look at this aerial image from Lancelin, you can help, or it may help you to appreciate how complex this system can be. So we've got a series of different reefs. You can see all the different directions of waves and the areas of wave breaking that help to shape what this coastline actually looks like, and it's a very complex area in terms of the wave transformations and sediment transport processes that happen in this area. But if the water level was to increase by a metre, the patterns of this wave breaking would change significantly, and as a result, it would be expected that the actual shape of the shoreline would also change as a result. So these are the things that make it more complicated to assess what the actual change due to sea level rise will be. There are much more detailed investigations that are required to better understand the extent of these changes, and that's why within the state coastal planning policy it does use this reasonably conservative assessment of a 1 in 100 slope using the Broome rule approach. So we've talked about the different sediment transport processes, and we've talked about the impact of sea level rise on the coastline. We now need to consider what that means in terms of the hazards that can directly result from these coastal processes themselves. So there are a number of different hazards that are covered within the state coastal planning policy and that need to be considered. The first of those is coastal erosion. So you can see in this figure, which is from Colleroy in 2016, a very well-known erosion event that had quite a lot of media attention. You can see that there is significant impact from erosion. You've got undermining of structures, you've got loss of structures. It's obviously quite a devastating impact that can be experienced. I have included a note there from the Insurance Council of Australia, just basically saying that insurers won't cover the action of the sea. It's a very common exclusion from insurance policies, and I guess it's something that we all need to be mindful of in coastal planning and asset management, is because anything that's built on or near the coastline is very, very unlikely to actually be insured against the actions of the ocean, so including coastal erosion. That also is commonly including coastal inundation, which is another of our hazards. The impacts of coastal inundation, or the potential impacts of coastal inundation, are quite obvious. You can see this photo here from Tropical Cyclone Yasi, and this is the photo of Cairns. If you recall, Tropical Cyclone Yasi was one of the events that we discussed when we were looking at the water levels, and had a total surge of 5.33 metres, so a very significant event. Undoubtedly, there's safety issues, and there's issues in terms of building structures and the likes that are associated with coastal inundation, so it's a fairly serious thing to consider. Not so commonly thought of in terms of a hazard is coastal accretion. So just to give you an example of where accretion is a problem, this is a small jetty that was constructed in Rockingham, and you can see that jetty sitting there in 1985. We skip forward to 2000, that jetty is still there, it's still functioning. I believe it was used by fishing vessels and the like. And then we skip forward a few years and we get to 2003. All of a sudden there's been a massive amount of accretion on the shoreline that's occurred, and that jetty now doesn't even make it to the water. So coastal accretion can very much be a coastal hazard for different assets and different infrastructure. And the last one is wave overtopping. So wave overtopping is where we have a wave hit a structure and it actually runs up and over that structure, or sprays up over that structure. It can be very serious in terms of it can knock people off their feet, it can wash people into the water. It is a very serious consideration for any kind of structures that are near the coastline, or even for natural rocky outcrops or headlands, because wave overtopping can occur there. A key point to note with wave overtopping, it doesn't have to be rough, or it doesn't have to be stormy for wave overtopping to be an issue. So again, just a photo of City Beach, and you've got an operator working on the top of the path at the City Beach groin. You can see an incoming wave. As that wave goes through, it ran up and over the groin, and you can see if someone was right on the edge of that groin and not ready for it, could certainly have had an impact on that person, and could have been a very serious safety issue. So something that we need to consider very carefully in all structures. So that's a very quick introduction to coastal hazards and what they are. I note here though that further details on the assessment methodologies for coastal hazards will be part of future CoastWA training modules. So we're not going to cover them in any further detail here, but there will be further detail provided in future modules. So now we try to tie together everything that we've been through up to this point, and just wanted to run through a selection of case examples to, I guess, try and bring it all together and to understand why it is important to consider coastal processes when we're working on or near the coastline. So the first example is from down at Albany, and what we want to look at is what can happen when we change wave patterns. So for those of you that aren't necessarily familiar with Albany, we have Albany sitting within Princess Royal Harbour. We have King George Sound that sits, I guess, to the east of Albany. And within King George Sound, we have a key tourist attraction, which is Whale World. So an old whaling station, which attracts a lot of tourists to it. The way that people get to Whale World is by basically driving from Albany around Princess Royal Harbour and out to the Whale World itself. There was an idea to try and run tours from Whale World, and part of that was to try and get an opportunity for boats to come in, so tour boats and or ferries to ferry people to Albany and back, to make it a better experience overall for the tourists. So this is what the area looked like prior to construction. We had a sandy beach, there was a small little boat loading, unloading facility, but that was very, very weather dependent. So there were some issues with it, and there was no reliable way to get people on and off those boats safely. So the construction occurred, which was basically building this breakwater at the end of the beach, coming off a rocky headland, and putting a pontoon in place that would ultimately allow the boats to come in, tie up, and be able to get people on and off the jetty in a really safe fashion. This photo was taken 1 year after construction, and you can probably already start to see the impacts that this facility had on the coastline. If you look at the position of where the beach was prior to construction versus where it was 1 year after construction, you can see there's been some very significant accretion of the shoreline in behind that facility. As we fast forward another few years ahead, you can see that that breakwater is now almost entirely filled with sand. They actually went through a process whereby they removed that pontoon and they built a different little jetty or wharf out on the end that you may be able to see out here. But even that is now getting inundated with sand. And 6 years after construction, the whole area was basically full, and there's no boating that happens in that facility, but what they have created is probably a really nice sheltered swimming beach. So why did this happen? Well, we've obviously changed the wave patterns in that area, and as a result, when the predominant waves come from the east, we've actually caused a diffraction effect where we've pulled some sand back into this area, and it has also probably trapped some sand that would be potentially moved as a result of seas coming from the west. So it's been very effective at trapping sand in that area, and it has created a very nice beach, although that was not the intention. The next example to look at is Port Beach. So this is, for those who don't know, just to the north of Fremantle Harbour. You can see Fremantle Harbour sits down here. We've got the Rouse Head extension here, and the moles sit just to the south of this, so the north and south mole into the Fremantle Harbour. You can see that the thing about Port Beach is that it has no feed of sediment from the south. It has a hard edge, it's Rouse Head, so there's no feed of sediment coming from the south. And really what you have is just an overall zone of beach that is potentially prone to impacts from seasonal variations in sand transport. If you have a look at these figures on the right, you can see from the end of March to the end of December 2014, there are differences in beach widths that result. So the end of March being the end of summer, there's obviously been sea breeze events which have pushed material to the north and resulted in a really narrow beach down at the south. At the start of December, so a bit later than the end of winter, but we're working with the availability of photos that we have. You can see that we've got a much wider beach here where that sand has been pushed back to the south due to those due to those storm events occurring. When we get to 2015, we've had the same thing happen in March at the end of summer. We've got a narrow beach, and in November we've got a much wider beach. So the issue with that is that we've got this seasonal transport that's happening that's more or less in balance. When we look at it in more detail, that Port Beach area loses about 10,000 cubic metres of sand per year on average to the north. What we focus on though is that in 2001 we had this period where we had a very small number of storm events, and as we've just seen from looking at those photos, the storm events are key in terms of returning that sediment to the southern portions of Port Beach so that we have, a wider beach that's then, all that material is then moved to the north again in summer. So you can see in 2001 that occurred. In 2010 we had something similar, and probably again in about 2015. What that means, so following this 2001 event, the volume is estimated that the Port Beach area lost about 60,000 cubic metres that went to the north in summer and wasn't returned in winter as a result of the small number of storm events. So instead of losing 10,000 cubic metres a year, it lost 60,000 cubic metres a year. And not long after that, there was a storm event. It was quite a severe storm event in 2003, but it resulted in significant erosion of the shoreline. And no doubt that was due to the pressure that whole shoreline was under as a result of losing that extra sediment from a longshore transport process because of the lack of storms in those years, bringing the sand back to the beach. So that's where, as I alluded to earlier in the presentation, you can have periods of actual calm weather, so lower number of storms, that can still lead to issues on the shoreline, because it is a delicate balance that a lot of these shorelines are in. Next example is from Jurien Bay. So we have an example here which is just from Google satellite images, Google time-lapse, which is another useful tool if you're looking along the coastline. This just shows the dynamics of the area in and around Jurien Bay. And you can see when I play this video, there's a combination of onshore feeds, there's the impacts of the marina, there's various things, but you'll see the variability of the different sediment transport processes that occur over this period. So when I play this video, you can see a very significant amount of movement around the eastern portion of Balanga Island. You can see these bars of sand moving. You can see significant changes to these salient features in the lee of Balanga Island and the sandbars that form there. And you can also see a significant increase in the volumes of sediment either side of the marina that was constructed in the 80s. So again, what does this mean? Well, in 1989, there were these jetties that existed at Jurien. In 2006, you can again see that, well, these jetties aren't as long out into the ocean as they used to be. And what does that mean? Well, it means that the shoreline has been accreting. The challenge for that was that the city wanted to ultimately the Shire wanted to ultimately get rid of those couple of jetties and replace them with a new jetty. And going through the design of that jetty, though, with the Shire, the one thing that was considered was the fact that shoreline was accreting at about 1.5 metres per year. What that effectively meant is that every year your jetty that you build would get 1.5 metres shorter because the shoreline was continuing to accrete. So you can see the consequence of that here in that you've had in 2012 quite a significant jetty length, and this area that I'm circling now was more or less the sort of the area that kids would jump in off the jetty and swim back to the shore or climb back out and jump in again. That area is now completely on the beach in 2023. And I guess the distance offshore is now much shorter, to the extent where you can actually see where the deeper water is. The head of the jetty is only just in the deeper water, and it's probably not going to be long until the head of that jetty is just entirely contained within the shallower water that sits behind it. So this is where accretion can be a problem. Like I said, it was known at the time of building the jetty. It was accepted that there wasn't much they could do other than sort of build the jetty and have to, I guess, deal with it when the time came. So moving back to Rockingham now, this is the Bent Street boat ramp, just zooming out to give you the overall picture of where this area is and where it sits. So it sits within Warnbro Sound. We've got Penguin Island, and again you can see a bar from Penguin Island. You can see these offshore sand sources that are coming in, but this is an area of pretty significant coastal change. And if you refer back to the images of the jetty that I showed that was impacted by accretion, that jetty was located just where the pointer is there. So again, using Google time-lapse, which is again a really useful tool, we can help to see what happens here. So if you note the existence of this bar, so turn bank, and how that changes over time as we play the video. So you can see it comes on shore. As it reaches the shoreline, we then have this interaction with the typical coastal processes, which results in a very significant and very rapid increase in the length of that bank towards the southeast. So I'll play that again. You can see the offshore bar comes in. Once it reaches the shoreline, these longshore sediment transport processes start to kick in as well, and it really starts to push that bar or the bank very, very quickly. So that's a challenging problem when you have a boat ramp that's sitting in behind this area and people need to actually access through a channel so that they can get to the ocean, because they now, City of Rockingham now need to manage that bank so that people can still get in and out of the boat ramp. So this brings us now to our final case study that I want to look at, which is Mandurah. So Mandurah is a very interesting area. There's a lot of different processes going on, and I guess it is a really good example to hopefully try and tie in all the things that we've looked at. So starting in the figure on the left, you can see in the 1960s there was a settlement within Mandurah, the Mandurah area, and there was the Mandurah Ocean Channel. So one of the things was that this channel was, I guess, subject to the natural fluctuations and natural coastal processes, and there were many periods over summer where this channel would naturally close, and you would end up with water bodies that were just not connected to the ocean. The challenge with that is that the groundwater from the septic tanks that were installed in these areas made its way into these pools, these stagnant pools, and eventually caused issues in terms of the water quality. So recognising that there was something that needed to be done, the Public Works Department ultimately came up with a design for some training walls to basically keep the mouth of this entrance open. It was acknowledged at the time that there was sediment transport along the coastline, and some of those estimates put that rate of sand transport in the order of 130,000 cubic metres of material per year that would need to be moved to the north. One of the consequences, or one of the things that happened with the design of those training walls, was that in the detailed design documentation it noted that there would be the potential for safe navigation in and out of that waterway over time. Following the construction of those training walls in the late 1960s, a fleet of fishermen actually started to use that area. Then over time, as the sand transport began to sort of build up and inundate those areas, there was more and more pressure to keep that entrance open so that the fishermen could get in and out safely. So they actually started a sand transport process to move sand from one side to the other. However, the other consequence that happened at the time was that the shacks that existed on these northern portions of the beach were actually transferred across to freehold title, and given the interruption in the sediment supply that had occurred, the beaches on these northern areas started to erode and put some of these now freehold title areas at erosion risk. As a result, there were some groins that were built, and also there was a significant amount of dredging that occurred within this area that you can see on the figure on the right, to actually place sediment onto these beaches to help stabilise the area. Obviously, that area now has become the Mandurah Ocean Marina. So with all of that background, what I wanted to show now was just a figure which I guess illustrates the changes that occur on a annual basis at Mandurah. So if we play this figure and it's just stepping through a series of images, you can see that basically at the start of summer you end up with this build-up of sand, and then it starts to push across into these eastern areas, and it ends up filling this sand trap. Then over time you'll see that the sand in that trap is removed and it's actually pumped through to this shoreline here. So you can see where that shoreline has a big slug of sand, that's because it's been transported from the western side of the entrance across to the eastern side. Now when they were doing the construction of Mandurah Ocean Marina, they actually sunk a pipe so that material can be pumped via pipeline from the beach on the west through to the eastern area in front of the Seashells Resort. But what you can hopefully see as we just look through it again is that you've got all this sand that's making its way up the coastline. It builds up into this big I guess salient feature. It's pushed in by the swell event as we get closer to winter, and then it really starts to get pushed into these areas within the sand trap before it's bypassed and then makes its way up along the beach, again providing a level of protection to the infrastructure to the north. So I guess that Mandurah example is a good example of where things can work and how there's a number of different steps that need to happen because there's been, I guess, an anthropogenic impact on the coastline. I am very conscious that some of these case examples that I've focused on are negative, but there are a lot of positive examples of things as well. They're just often not as good at explaining why it is important that we consider coastal processes in the various coastal planning or coastal designs that we complete. So that concludes the coastal processes section. Hopefully that's been a useful introduction to coastal processes and helped to outline why consideration of coastal processes is important for coastal planning and coastal management. Thank you.